Okay, 91577, apply the algebra of complex numbers in solving problems, the 2025 examination. This is take 3 or maybe take 4 of me attempting to make this video. I'm looking only at question 2. The first time I tried this, my video failed a few minutes into the recording and I didn't notice. The second time I managed to not capture the whole of my OneNote screen and I just had a false start a couple of minutes ago where I'd loaded the wrong file. So let's hope for some good luck. So question 2, the locus, no, that's question 1. The complex numbers, part A, the complex numbers U and W are represented on the Argon diagram below. If Z equals 2U plus 3W, find Z and clearly show it on the Argon diagram. So we can start by identifying these complex numbers. So U is 1, 2, 3, 4 across and 2 up. So it's the complex number 4 plus 2i. And W is 1, 2 back, that's negative 2, and then down 3 minus 3i. So we've identified those two complex numbers, and then we just simply have to do some relatively straightforward algebra. 2 times 4 plus 2i plus 3 times minus 2 minus 3i. I like to collect together the real terms first and then the imaginary terms. So 2 4s are 8, 3 times minus 2 is minus 6, plus 2 2s are 4, and 3 times minus 3 is minus 9, all of that times I, so we get 2 here minus 5i. And that's, I think, reasonably straightforward. The question does say, and clearly show it on the Argon diagram below, so we have to mark this point, so it's 1, 2 across, 2, 4, 5 down. We've got this point here is Z, which is 2U plus 3W, which is 2 minus 5i. And that would solve the question. I think they could have been kinder to us in the question. Kinder, not in terms of the algebra that we need to do, but in terms of the diagram, because you could do this addition visually. So if this is U, then we could go out here to find 2U, but we're outside the graph. And then if this is W, then going back 2, down 3, back 2, down 3, back 2, down 3, 3 times will give us the 2U plus 3W. So you could have done this graphically, and for you to do that, it would be better if the graph was extended so that you could fit all the working on the graph. In any case, you get the same answer both ways. B, this looks like a straightforward application of de Moivre's theorem. So U to the power of 5 is equal to M cis 3 pi over 10 all to the power of 5. And de Moivre says take this modulus and raise it to the power of 5, and take this argument and multiply it by 5. So that's 15 pi over 10, 3 5s are 15, and we can do some simplification, divide by 5, divide by 5. So we get M to the power of 5 cis 3 pi over 2. The question though does ask that we want the answer in real imaginary form, Cartesian form, and we've got it in polar form. So we need to convert this to real imaginary form. For this question, I think the easiest way is to draw a picture. This angle round here is 3 pi over 2. That means that this complex number is somewhere on this imaginary axis, and in the negative part of it, because we're down in this region. And how far down are we? Well, we're exactly m to the power of 5 down, negative m to the power of 5i sits exactly on this line. So we could write this as negative m to the power of 5i, and that should be an answer. You could put the 0 plus negative m, because they did ask explicitly for that form. I don't think you'd lose any credit for not putting the 0 in. Question C, we want the modulus of 5 minus mi is equal to the square root of 5m squared, and it says m is a real number, so this number here is just a complex number. The modulus, if we have a plus bi, remember that's simply the square root of a squared plus b squared. So over here on the question, we can rewrite this left-hand side as the square root of 25, 5 squared, plus m squared, which is negative m all squared. And that has to be the square root of 5m squared. We haven't got any problems here. Both these numbers under the square root are positive. M squared is always positive. M squared there plus 25 will also be positive. So if we've got two things that are both having the square root taken to them and they're equal, then the two things under the square root must be equal. We can take off the m squared. That will leave us with 4m squared is equal to 25. That means m squared is 25 over 4. And that means in turn that m is equal to plus or minus 5 over 2. And we're done. Part D. We've got an equation that involves complex numbers. The basic strategy to do here is to multiply out the brackets on both sides and then equate the real parts and equate the imaginary parts, and that will solve the equation. Typically you'll get a system of two equations that need to be solved simultaneously. So let's start. I like to multiply out the real parts first, so we get 3g, and these two give us a real number as well, 2h, and I squared is negative 1, so you get minus there, and then do the imaginary parts. So the imaginary parts is g times hi, and 2 times 3. Oops. That's the left-hand side. Do the same thing on the right-hand side. 10 times 3 is 30. 4 times 1 is 4. Minus times minus is positive. I times I is negative 1, so it's going to be minus 4. And then minus 10i minus 12i. So plus minus 10 minus 12i. We can tidy that up. That's 26 minus 22i. And now we can separately equate the real part and the imaginary part. So the real part gives us 3g minus 2h has to be equal to 26. And the imaginary part gives us gh plus 6. Keep hitting my eraser button. Equals negative 22. That's the same as gh is equal to negative 28. And it's going to be useful for us to solve this to write g or h as the subject of this equation, and then take this value and substitute it into here. So what do we get? We get 3 times negative 28 over h minus 2h has to be equal to 26. Now this is a quadratic, sort of a quadratic in disguise. If I multiply the whole equation by h, I'm going to lose the h here, so that's 3 times 28, 60, and 24 is minus 84. Multiply this by h, you get minus 2h squared. Multiply this by h is 26h. You see it's a quadratic. Write it in standard form, and I'm going to simultaneously divide everything by 2. So we get h squared plus 13h, putting these terms onto this side, plus 42 equals 0. That's got an easy factorization, h plus 6, h plus 7. 6 plus 7 is 13, 6 times 7 is 42. So we've got h equals negative 6, or h equals negative 7. We'll go up here. If we look at h equals negative 6, we get g is equal to negative 28 over negative 6, which is 14 over 3. And if h is equal to negative 7, we get g is equal to negative 28 over negative 7, which is 4. And that's the two solutions of the equation. The two solutions involve both the h value and the g value, both the h value and the g value in each case. Part E. We're told the argument of some complex expression is equal to pi over 4. I think it's very useful to think about what that means, to think about what that means in terms of the argument pi over 4. And what it means is where our complex number is somewhere on this diagonal line, and all the points on this diagonal line are points where the real part and the imaginary part are exactly equal. So to solve this equation, what we want to do, if we called our complex number z, we want the real part to be equal to the imaginary part, and we want the real part to be bigger than 0, and if you like, the imaginary part to be bigger than 0. But if they're equal, they have to be both bigger than 0, if one of them is. Now, there is a continuation of the diagonal line down here, but the points down here have an argument of 5 pi over 4. So we want to be on this positive portion of this diagonal line, y equals x, basically. So what do? We take our complex number and we figure out the real and imaginary parts and then equate them. So standard practice is to multiply and divide by the complex conjugate of the denominator. That gets rid of the complex part in the denominator. So on the top numerator we get d times d, and we get 6i times di. 6d I squared is negative 1. That's the real part there. And then plus the imaginary part, d times d is d squared, and 6 times 1 is 6. That's the imaginary part. And on the bottom we get 1 plus d squared. The mixed terms cancel. Di, negative di times 1 and 1 times di, they cancel. 1 squared, d times d is d squared. It's got a minus sign, but we've also got an I times I, which is another minus sign, so it becomes plus d squared. If we're equating the real and imaginary part, it's enough to equate the two bits that are in the denominator. The numerator. The denominator is positive, and that's not going to change whether these are equal. So two fractions basically are equal if their numerators are equal. So that means we've got, quite simply, d minus 6d is negative 5d, has to be equal to d squared plus 6. standard form, that's going to be d squared plus 5d plus 6 is equal to 0. So d plus 2 times d plus 3. Another relatively straightforward factorization. So d is -2 or d is -3. We need to check whether the real parts and imaginary parts are positive. So d is -2. The real part is, we're always going to be positive on the bottom. So we're going to have -2, well, -5 times -2 is +10. If you wanted, you could put this over 1 plus 4, -2 squared over 5. But you can see that doesn't change the sign. And if d is -3, our numerator is going to be -5 times -3, which is 15, which is positive. So both are valid. And again, you could put d's 5, 1 plus 9, so you put that over 10, this over 10. But all we're interested in is whether they're negative or positive, and both of these are positive, and calculating the denominator doesn't change anything. And we can see it doesn't change anything because the denominator is always positive. So dividing by a positive number is not going to change the sign of the whole number. The whole, not a whole number, but the entire number. And we're done. That's question 2. So any questions, put them in the comments. Otherwise, I'll see you next time for question 3, and hopefully it won't take me 3 takes, so I'll get that out sooner rather than later.